Thanks for the opportunity to speak. I'm Ian Hussey. I'm a senior lecturer at the University of Bern in Switzerland. Um, One of the last questions was the best introduction I could have hoped for, basically, on like how do I get involved? Um, that's something that concerns me a lot and is, I suppose, the subject of this talk. My various efforts to try and make this work more accessible, because I think there are a lot of hobbyists and disgruntled folks whose energies could be channeled into this. I'll talk to you about normalizing error detection and trustworthiness assessment. I'll start with an analogy here, which is like, what is the difference between the incredibly successful 2010s replication and open science movement and the kind of still nascent 2020s forensic meta science movement? I would say that it is the normalization of grassroots participation in this sort of thing. Now, that's not due to just failure to act on our behalves or anything as a community. There are definitely very different structures in place, and that makes this harder. But nonetheless, I think the success of the 2010s replication movement um, can be learned from. And I want to try and channel, I'm working hard to try and channel those same energies into making this type of forensic meta science work easier and more popular. So I think James has already done a good job, as he always does, of selling the scope and scale of the problem. I'll touch on it very briefly and then try and get to what do we want to do about it. Um, I think it's useful to recognize how much, as James said, we have been operating from a trust-based system for so long. The editor of Science back in 1987 said that 99.9999% of reports are accurate and truthful, and that there is no evidence that we require any fundamental changes to our procedures that have produced so much good science. This was in response to a specific fraud scandal at the time. Now, I cannot help but read this and think that this is just the definition of hubris. And the last few decades have won out that this was incredibly over optimistic to put this rate so high. So I think we are moving slowly but surely from this perspective that science is self-correcting to the idea that it is, as Samin Vazir said, that it's only self-correcting when we correct it. It's not a magical process. It's not a that it has some agency to it and that it involves no human intervention. It is self-correcting when we self-correct it. So in the last few decades, and accelerating over time, we see more and more articles saying not that uh, that the accuracy and truthfulness of work is 99.9999%, but rather much, much lower. That the rate of negligence, of fraud, and of error, which are related but distinct, depending on how you want to look at it, is much higher than this. We have increasing number of articles uh, with titles like there being a worrying amount of fraud in medical research, or simply fraud, so much fraud, asking where are the self-correcting mechanisms in science? The former editor of the BMJ wrote a few years ago that maybe it's time to assume that health research is fraudulent until proven otherwise. So this is not a trust-based system that people are calling for anymore. It's a trust but verify one. And the consequences of these errors, negligences, and fraud are far-reaching. Like usually I start talks like this with a long spiel that I don't have time for today about how I, as an Irish person, was affected by this too, about George Osborne and other world leaders plunging the UK and other countries, including Ireland, into austerity based on spreadsheet errors, right? Errors in Excel formulae were the basis of the austerity policies following the Great Recession that still impact our countries today. And a great paper by Wolfgang Strobe talking about how the self-correction mechanisms in science, such as they do exist, seem to be seem to happen outside of our formal structures. They rely on whistleblowers and yeah, disgruntled, dyspeptic folk like James. And this is not ideal. To sing James's praises further, he wrote a very, very interesting article last year, um, coming out this year, where he argues that perhaps the rate of fake papers in science is as high as 1 in 7. And as he takes quite a lot of time to say in that article, and I think critics of the article should also bear this in mind, is this number, this 1 in 7 number, is not a literal claim, but the argument that we are acting as if, collectively acting as if, the rate of error, negligence, and fraud in science is 99 point, a tiny fraction of 1%, that almost everything is correct. And in fact, it is likely much, much, much higher. Now, do we know what that proportion is at this moment in time? No, but we need to start acting as if it is as high as 1 in 7. So we should take this point seriously, if not completely literally. When I teach students about this, I tend to mention to them early on that it is surprising that academia and science, as the industry whose primary output nominally is truths, that we have so few quality assurance mechanisms. If I buy pasta in the store, there are far more checks and balances gone into ensuring the quality of that product than there are in most scientific papers, which are entirely, almost entirely trust-based at the moment. So too much of scientific truth is currently being held up by 2 to 3 peer reviewers, often doing these reviews on a layover flight between two countries, lacking in sleep on their way to or from a conference. And this is very strange, to shunt most of our quality assurance to this one, usually non-technical review process. Let me give you an example of what I mean here. It's not just that peer review needs to be better. It's not just that we need more mechanisms. We need levers to pull on when things are knowably off the rails. When things have gone wrong, we currently often can't do anything about it because of the ways that science currently works. Take, for example, this paper on the effectiveness of nudging, which was published in PNAS a few years ago. This is the forest plot from their, sorry, the, what do you call it? Not forest plot, funnel plot from their meta-analysis. And within hours of the article being published, screenshots of this were circulating around Twitter, and people were calling nonsense on it. Now, perhaps for those in the audience who don't have an intuition for Cohen's d, um, Cohen's d's in psychology above 2, effect sizes like that are very, very rare. You tend to only see them with manipulation checks when you ask people like, are these positive images more positive than these negative images? Really, really basic stuff like this. Cohen's d's up at 4 and 5 almost don't occur except for truisms. One example I can think of is asking school children, do boys tend to wear skirts more often than girls tend to wear, sorry, the other way around. Do girls tend to wear skirts more often than boys tend to wear skirts? These things that are sort of norms in society around us. Positive images are positive, disgusting images are indeed disgusting. Um, Trends and norms in gendered dressing tend to be adhered to on average. There where you might see Cohen's d's of 5. To see a Cohen's d this large is just not possible. Now, the problem here is what do you do about it? Even when you know this is the case. Usually when we would approach authors and say, these numbers can't be real, you have probably made a mistake, they say, we weren't aware. That was different in this case. People went to them and said, not only these effect sizes are too large, but they are produced by studies published by Brian Wansink. And Brian Wansink famously had to take early retirement, quit his job because he had so many retractions due to fraud and malpractice in his work. He made up a lot of data in his early career, and then published a blog incriminating himself, talking about how he encouraged all his students to p-hack. And the response here was very strange because the authors said, well, these effect sizes in the plot are not from retracted studies. So we know Brian Wanson's work is suspect, and we did not include any of his retracted work, but this work isn't retracted. So point to me somewhere uh, in the Cochrane Handbook or another guide for doing meta-analyses where it says that I'm allowed to arbitrarily delete studies. There really isn't one. We lack a lever to pull on here to say everybody in the room knows there's a problem with this work. So how do I stop it participating and entering into our knowledge syntheses, right? It's not just a lack of time and resources. It's not just lack of community, although these are all problems. We need levers to pull on to allow ourselves, for everyone in the room who knows there's a problem, to say so. So as Malte Elson, who I work with here in Bern, said in a recent piece in Nature, science must realize that making error detection and correction part of the scientific landscape is a sound investment, right? It has value, as much value as being able to assert that something is the case. It is useful to be able to say that something is not the case and something should be ignored or excluded from evidence syntheses. But this is currently much harder to do. So we need normalization efforts, and this is something I spend a lot of time thinking about. I liked Brian Nozick's model in Center for Open Science for this so much that I keep stealing it and using it in different ways. The general model is to make things possible, to make them easy, to make them normative, and eventually make them required, although that's a policy level thing. How would we do this within error and trustworthiness assessment? Well, first you need to make it possible, as in to recognize that issues exist, and even that is a massive effort to communicate the scale of the problem, as James says. And then you need to provide methods by which other people could detect similar things so that everyone isn't starting from scratch as a hobbyist, a sort of sleuth hobbyist wondering, how would I critique this? And then you need tools to do it, like R packages that make these things easier. And these methods need to be validated so that if you present this evidence to other people, they don't have to be argued for from first principles. You need to make these things easier with guides, tutorials, web apps, and dissemination methods like PubPeer. And then you also need to make it normative. You need to integrate it into our teaching and into our research process so that it's less so done by some slightly obsessive oddballs like myself, James, others, and more so done as part of master's theses, as part of PhDs, as an investment. In the same way as 10 years ago, 15 years ago, it was a fairly radical idea that PhD students, before starting a multi-year research program, should replicate the study that they're seeking to extend and build upon as a sort of, can we rely on this enough to try and build on it? So too must it become increasingly normative that researchers say, let's look for errors and trustworthiness of this work before I spend multiple years of my life acting as if and assuming that it's legitimate, when maybe it's not. Maybe there are mistakes in there. Maybe these are completely legitimate, accidental mistakes, up to things that are, more serious. So I'll talk for the rest of this talk about these 3 points. First, the make it possible one, and then the make it easy and make it normative one. What does making it possible look like? First, you need to recognize the problem. This is something that takes entire classes worth of expounding the scale of the problem. I think James did a great job of doing of introducing you to it in the last talk. But here in Bern, we run entire semester-long seminars for master's students just on introducing the problem without providing any solutions to it. So this is a big problem. You also need to be taught, once you know that there is a problem, you need to know where to look for these problems and how to look for these problems. So I will keep my recognition of the problem slide to just one because it's a very useful and orientating exercise for me in most work that I do. First, you have to train people, including yourself or your students, to be willing to consider that errors, negligence, and fraud exist. Because as you saw in that 1987 Science editorial, many people are still acting from the position that they do not consider it to exist, right? Any discrepancies in results between papers are assumed at worst to be sort of moderating conditions or perhaps non-replicability of certain studies, but not just outright error or negligence or even fraud. And once you're willing to accept that they exist or consider that they do, it's useful to think under what conditions they occur. Usually, and I shamelessly took this from a TikTok video. I wish I could claim that I got it from somewhere more sort of lofty, but I saw a TikTok from a science communicator where she talks about the most serious scientific errors occurring in situations that are both boring, complicated, and consequential. And I think this is very, very useful. This is the blind spot most of us have. Even with things like the George Osborne spreadsheet error that is extremely consequential, but it's also very exciting, right? It's not boring at all. It is also not even complicated. The hardest errors, negligence, or fraud to find are the ones that are all three of boring, complicated, and consequential because they take the most kind of effort to look into. So imagine you are a hobbyist sleuth without much experience on this. Um, And you have come across such a thing, perhaps in your own work or because you have cast around looking um, for errors in the wild. Where would you look? What do we have access to typically? There are many outputs of the scientific research process, the most common of which obviously is the article, which is usually available, but not always. It could be old or it could be gray literature. You also have the measures, the data, and the code. And these can all be inspected individually. This is, in one sense, incredibly obvious, but right now there's not too much of a guide documenting that this is the case, that there are very, very different ways of looking for error, negligence, trustworthiness assessment on each of these elements. And they're very different methods, and they depend on what you are trying to look into. Is it the measures themselves? Is it the code? Debugging code and finding errors in code is its own skill set. Is it the raw data that you have been given access to or is already available? Finding evidence, especially of fraud in raw data, is a whole class of statistical measures. Or is it looking, starting off with the article and examining that? These don't exist in isolation, of course. The measures tend to generate the data, which is analyzed usually with code, hopefully these days, and published in an article. So they are interrelating and they have correspondences with among one another. And all of these provide opportunities to look for inconsistencies, right? If the description of things in the article is different from what is actually done in the code or the structure of the data or its contents, these are all checks on consistency that you can do. Again, as well as there being um, a variety of methods for looking at these in isolation, there are a separate variety of methods for looking at them in combination. Some of these already exist. Some of these need to be fleshed out further. And this is all sort of current fruitful areas of work for forensic meta science people. There's a tension here. There's a tension because the article is the most available one, but especially if you are a sleuth type looking for outright fraud, the most useful one to you is the data itself. But of course, the data is usually not provided, right? I've published work on this myself. Data sets across time and space and areas of research are usually only provided on request about 3 in 10 times, so about 33%, 33% of time. Even when the authors themselves tell you they'll give you the data, and the journal requires that they do, and their university requires that you do, and everyone else requires that you do, people usually don't share it. And I would guess that people who have something to hide share it at an even lower level. So on the one hand, the data is where we probably should be looking, but we often can't look. And the article is easy to look at, but often you have to look for hints instead. So the article is where you should start, but it's probably not where you should finish. Nick Brown, who you'll hear from on Thursday, I think, talks about these types of methods as party tricks done with articles. And I think it's a great phrase. His line, as of recently, is that we should be moving away from this, and we should be empowering editors and encouraging editors to demand access to the data directly. I totally agree, but it will also be years until these things improve, right? Science is slow moving. Data sharing took us several years to get off the ground. Demanding data from people who aren't inclined to share it is going to take years too. So I still think these party tricks are very useful, and I spend a lot of time thinking about them. And I'm going to talk to you about one or two specific ones here. So what do you need within the article? You need things that are commonly reported. They can't be super crazy rare that it's never useful to you. Usually they involve information that is repeated or overlooked or both. Again, that's a Nick Brown phrase that I've stolen. It needs to be accessible and easy to check, and it needs to be usefully diagnostic of deeper issues if they exist. So these are all ways that we can orientate ourselves towards what is useful to look at in an article and what is less so. Now, what are some of these? Well, combinations of sample sizes, means, standard deviations, and ranges are surprisingly useful, as well as test statistics and p-values and effect sizes. In particular, sample sizes, means, standard deviations, and ranges are the sort of thing that are reported, but they are completely overlooked by even the authors, right? And this is particularly useful where especially it seems to be the case that negligence and fraud is associated with sort of imperfect understanding of these things themselves. So we need some average ages or some average scores and their SDs. And in extreme cases, these are sometimes just made up, right? There is no underlying data set. And as a result, there's ways of suggesting that this might be the case in order to then cast a closer look. The problem here is that we have an issue of what's the phrase? Of expertise. It takes expertise to look at this ANOVA F test or any of these means and standard deviations and be able to spot if any of them are problematic or not. Now, I can't see the audience, but can anyone raise their hand or shout out, are any of these problematic?
We had one hand
raised. Yes, 38.2 standard deviation of the age.
So the age
was
flagged.
38.2 standard deviation on a mean age of 23.1.
And what's your intuition for why why something is wrong with that?
Well, how can you be a standard deviation on 38.2? That's too far from a 23.1.
Yeah, it would require some incredibly old participants in the sample. But this sort of thing is included in articles. And more importantly, I think many readers gloss over seeing means and standard deviations. When I ask at least my rooms of master's students, what's your intuition for too large or too small a standard deviation? Most have very poor intuitions for it. If I could see and ask around the rest of the room, I'm not sure how many others would be able to spot that SD for age is too large. Equally, for the PHQ-9, that standard deviation is also too large. And for the BDI, it's mathematically possible that standard deviation could be that low, but it's incredibly implausible. I spent a lot of time reading into depression papers over the last few years, and so I have an intuition for the BDI. I can look at BDI data and say, The SD should be between 8 and maybe 12. A sort of 5 would be a very, very low SD. 2.3 is implausibly low, especially for that mean. But this isn't a scalable way of doing things, right? How many domain experts would you need to know the Beck depression inventory that well, right? We need more general tools so that, of course, domain expertise is very, very important to doing deep critique, but to make progress at sufficient speed, you also need methods that aren't entirely shackled to that domain expertise. So in all cases, there's something wrong with all of them. That p-value isn't possible given that degree of freedom and that test statistic. The PHQ-9 SD is too large, the BDI is too small, and the age SD is too large. But how would you know this? There is a surprising amount of information hidden in tables and plots and text provided by most articles. If you have the sample sizes, which this particular article has in table 1, and the means and standard deviations in table 2, they have effect sizes in table 3, and they have ANOVA interaction effects and main effects listed in the text itself. Once you start learning about how much you can do with all of these things, the interrelationships and the dependencies among these numbers, it's quite startling. And once you start checking for them, for the simplest things that should add up and don't, you start to become a little depressed about the state of the literature. So for example, the total rows here are just the weighted average of the subgroups above them. So the 36.56 on the left, the average there, we have the means from table 1 above it, and if you weighted average those means, you should get the total weighted average mean, the 36.56, and you don't, nor do you get the other two ones that are circled there, which maybe by itself is just a typo. And I don't know what it is in this case, but I know that the numbers don't add up. I can also point out that the means are not consistent with the sample sizes. Those means are not possible with the ends listed in the table above. This is checked via GRIM, which you'll hear more about. I can also check whether p-values are consistent with degrees of freedom and F statistics. In this case, all of them are, so I haven't circled any problems. You can check this with StatCheck. You can also, I wouldn't have known this a few years ago, recalculate between subject ANOVAs just from the means, standard deviations, and ends. Just the cell counts and their distributional data can allow you to reconstruct the ANOVA as a whole. And in this case, it seems that the ANOVA results for these two conditions, the Hispanic and the African American conditions, have been swapped, or something has been swapped. Perhaps it's their sample, their means and SDs. So these aren't possible given the N, M, and SD. And equally, you can use the means, SDs, and ends to recalculate the Cohen's d values, and none of these are possible. So either the effect sizes or the M, N, and SD are wrong. You can keep going with this stuff, but it's fascinating to me once you are given this toolkit of, well, I could just check this against this, how much you can check, how you can do it relatively quickly, and it can be not an end in itself, but a strong reason to look deeper to say, well, the simple stuff isn't checking out, so maybe we've got deeper problems. Maybe it's time to request the data sets. So you're going to hear about GRIM testing, granularity testing from Nick in detail in a workshop context on Thursday. But let me tell you about some of the work that I've been doing to try and bring together GRIM, its extension Grimmer, and my own tool, or sort of my own tool, Tides, which is also built heavily on James's work on umbrella plots. The idea here is that we want to make the target that authors have to hit as small as possible. Okay, there are only a subset. If I was to randomly generate means and SDs for my work, or I'm generating them erroneously because I'm forgetting some digits or have typos in there, I want as few as possible false negative results, right? I want to be able to spot as many as possible impossible results. So I want to make this target as small as possible so that it's hard for error, negligence, and fraud to go undiscovered. So imagine this common use case that we have of a single item 1 to 7 Likert scale. These are incredibly common in psych, as Mairead Shaw's work showed recently. Imagine that I have a sample size of 31 because this is the median in psychotherapy for depression RCTs from Pim Cowper's data, and that mean and standard deviation are reported to 2 decimal places. I only have these 3 bits of information, the n, which is fixed, and then a range of different possible means and standard deviations. What could I do with this? How likely is it that just randomly generated values can pass different tests to check whether they're possible or plausible? What could we say about this? If I might do this in a more interactive context, if I could see the audience. But what we can say is that the mean has to be between 1 and 7. Yeah, because the individual data points themselves have to be within 1 and 7. This sounds so obvious that I really have to point it out twice to students, because obviously the mean has to be within the range. At the same time, ask yourself, how often have you checked this in articles that you read? When you see data was collected on this 0 to 63 point scale, the BDI, and the means are the following, 64. That can't be right. Start checking this in future in the papers that you read, and you will be, well, hopefully you'll be pleasantly surprised and find nothing. I start doing it, and I now see bounds violations everywhere around me. Bounds violations for standard deviation, it turns out, are more complex, having had to think about it for the last year. Maybe you do or do not have intuitions for it. I certainly did not a year ago. The bounds of standard deviation are between 0, because that's the lower bound of SD, to the range of the scale by the square root of 2 divided by 2, which is about 0.707. So for a 1 to 7 scale, in the smallest sample size possible, which is 2, the SD has to be between 0 and 4. Now, this is a very slightly mathy, but it's also incredibly useful. I had no intuition for this, but give this intuition to people and suddenly you can read articles and just with the calculator on your phone check, is that SD plausible? And this can be the min-max of the scale, or it can even be the empirical min-max, or even a kind of guesstimate of it. So for age, you can say, probably there's no participants over 100 or 110. So let's use that as the upper, and usually the article will tell you the lower bound is, say, 18 or whatever. And you can work this out, and you start spotting all sorts of weird results, which might cause you to look deeper into it. Even within these bounds, there's about 250,000 combinations of mean and SD, right? If they increment by 0.01 each, so the mean can go up 0.01, 0.02, and so on from 1 to 7, and the SD can go from 0 to 4.23. About 255,000 possible combinations of mean and SD. So how many of these are really possible? We can start by thinking about their granularity. I will save time here and not explain granularity in any depth. You will hear about it fully from Nick. The granularity of the means, which just means that some means are simply not mathematically possible, means you can get rid of a big chunk of these. I can't see the percentages. 1 second, sorry. My own slides were not visible. Okay, we can get rid of about more than 2/3 of possible means just by thinking of the granularity of that mean and applying the Grimm test. This is already incredibly useful, even though randomly generated means will still be right in about 1 in 3 cases. Why is this? Because most articles report lots and lots of means. So if you have 10 different means reported in the article with this sample size and this range, the chance that all of them are passing is still quite low. All you need is multiple means. And James and Nick put this to the test in a 2017 paper, which he will talk to you about in more detail, where they examined a few hundred articles, of which 73 qualified as checkable with Grimm, because sample size has to be lower than 100. And in them, they found 16 articles contained more than 1 grim inconsistency, and clarified later that 3 of these articles required significant correction. Possibly more also would have had the authors and editors insisted on data sharing. So this test alone is showing that 4% of articles have extremely problematic numbers requiring at least a correction. James clarified in his more recent publication that some of these looked, more like they were heading towards the negligence or even fraud cases. How much further can we push this? This was kind of my question to myself. Can we build, in order to make it possible to detect these things, how much further can we push the boat out on making the target as small as possible? Well, Nick has already done this with, and many others, with Grimmer by considering not only the granularity of the mean, but also the SD. He'll explain the method more, but this gets rid of even more of these values. Lots and lots of these pairs of means and SDs are simply not mathematically possible. You can get rid of 82% of them. So the insight here for me was that we should separate not just granularity testing, but also bounds testing. So in the plot I've shown you, it also has some means that are below the scale range, and these will still pass Grim and Grimmer. Right? Ones that are not visible cannot be observed on the scale because they are a mean of below the minimum point, will still pass Grim. Same, the ones above will pass. And also you can find standard deviations either below that global mean, global bound, or above the global bound, which will pass Grim and Grimmer. So excluding these gets rid of a few more cases. From 18% of them down to 17%. But these are what are called the global bounds, right? It still has things in the top right and the top left hand of the green area. If you consider what's called the local bounds of standard deviation, which requires a bunch of math and visualization to explain, and most people roll their eyes and fall asleep. So I won't go into it now, but you can work out the maths of the local bounds of SD, which get rid of even more of these cases, down to the point where only about 6% with this sample size of cases of randomly generated mean and SD pairs are actually possible. Everything else fails it. This is very, very useful at this point, because if I now have a 6% false positive rate, and I get to check multiple pairs of means and SDs and ends, the chance of erroneous or illegitimate work reliably passing these is now vanishingly small. So the combination of these bounds and granularity testing through Grimmer and my tool Tides becomes increasingly useful. And it has other advantages, like Tides still being useful when the sample size is above 100, which Grim can't do by itself. There are also still some more frontier efforts that I'm working on with others like Lucas Young and Nathaniel, like their implementation of their closure algorithm, which gets rid of a few more of these to say, even though they're Grimmer and Tides consistent, you actually can't construct data sets that have these means and SDs. We squeeze just a little bit more out there, 0.1%. So that's what the true umbrella plot looks like, as James called it when he invented them. And you can also push the bounds out further by saying, not just are these values possible, but are they plausible? So the difference between this plot and this one is that it gets rid of distributions that would have to have bimodality in them. Maybe that's plausible in some data sets, but usually our analytic methods assume it's not occurring, that you have two groups in this data set effectively with totally different means. So we can keep squeezing this down and down and down further. That's the goal here, to make the target as small as possible. But if we want to make it as easy as possible, right? The umbrella plots are not easy to interpret, and the maths of it are a little tricky. So I put a lot of effort over the last year in trying to make this more so through range-based standardization so that you end up with a plot. I don't really have a name for it yet, but a tides relative location, relative dispersion plot. The nice thing about these is that they are on a scale from 0 to 100 of what's possible. So is the location, the mean, possible on the 0 to 100 scale? And is the SD possible on a 0 to 100 scale? The very nice thing about this is it strips all expertise that you need with a given scale to know what the range of that scale is, or what the normative distribution of data on it, or what shape or skew it has. It temporarily removes that necessity from you so that you can take data from, for example, meta-analysis forest plots, plug it into the tides functions, and it will spit out a plot like this that clearly flags values that are not mathematically possible. So the ones in blue are simply outside either the mean or the SD that is possible for that scale. You can also bring together scales of different ranges and different sample sizes, which you can't do in other methods, so that you can plot dozens and dozens of RCT's data here and see what's impossible in blue or what's technically possible but highly implausible in red. So this data is real data. It's taken from the MetaSci data set of from Pim Cowpers on psychotherapy for depression. This data is being used in dozens of different meta-analyses of the efficacy of psychotherapy for depression, right? Many, many publications have come out of this. They continue to update its data set. It's a very, very, very valuable resource. But because it's so important, I think it's important that we now spend time considering, are all the data sets in it trustworthy? And some of these ones that are in the data set and are being used in meta-analyses, the summary statistics used to compute the effect sizes are either impossible or implausible. So with a master's student this year, I had a pilot study run on this where we took some of these most extreme values, the 10 articles with the most impossible or implausible value screen, and we found much deeper trustworthiness concerns in 9 out of 10 of cases. I've already had one of these retracted, but I had been looking into it for a year or two before that, and we'll keep looking into these ones now. And the goal here is to both make this tool more accessible for others, but also to use it practically to clean up these important data sets that are being used for meta-analysis. Okay, if you want to check out Tides or any of the other packages, Scrutiny, Unsum, or StatCheck, you can find links to Shiny apps for them and the R packages either on GitHub or CRAN. So a lot of my efforts these days go into trying to make this work possible in the first place, which is more stats heavy and technical. But after that, especially with regard to the question after the last talk of like, how would I get involved? This occupies a lot of my time. How do I make this stuff easier and how do I make it normative? Where would we learn these methods? How would I organize my activity and help organize with others in a social sense to do this type of work? How would I build community to do it? Dorothy Bishop, 18 months ago, wrote a blog post pointing this out, that there is a conspicuous absence of sleuthing methods, of forensic meta-science methods from our curricula. I certainly, well, basically everybody goes through their degree, their master's, their PhD, and even their postdoc without any training in a formal sense of like, how would I deeply look into this paper to know whether I can trust its findings? It's stunning to me that we, until now, don't have training on this. You are taught how to run a study, and you are given general kind of critical thinking skills, but not specific methods of critique or how to communicate that critique. And if we want science to be a self-correcting enterprise, we need to build in teaching on critique and communication of that critique into our curricula. So I was very happy to be able to reach out to Dorothy at the time and say, we are now teaching, I am now teaching that course at the University of Bern. So as much as, and I'll come back to that course in a second, as much as James has painted a vivid picture of the difficulty of the timescales and the psychic damage of doing this work, I would say that it is getting much, much better. 5 years ago, especially 10 years ago, there was no community for this. There was no even label for the field. Forensic metascience as a concept didn't exist. There were no teaching resources. The methods didn't even exist yet. James and Nick had to invent most of them. And that is fundamentally different now. Not only is there a sort of flourishing set of tools, but also of resources, training, and teaching on how to use them, and then what workflow to build them in, and how to communicate results around them. And I think this element of things is very, very important. I'll point you to just these three. COSIG, you'll hear from Reese in a few days, and he will tell you all about COSIG. It's a set of guides on how to use methods like this and communicate with them. Very, very useful, open source, grassroots organization. Please consider using the resources or contributing to them. There's also James's book, Forensic Metascience, and an Introduction to Forensic Metascience. Very, very useful resource. Probably the first book written on forensic metascience. And also incredibly important is Jack Wilkinson's work, who's based at Manchester, on Inspect SR, which is a tool that helps you integrate the results of different tests like GRIM, TIDES, and others into a global assessment of a piece, and helps lend it kind of organization and credibility. The biggest potential future win here would be Cochrane endorsement of Inspect SR, which is not impossible that it will come once the tool is validated. This would mean that, as part from having to do systematic searches and Prospero pre-registrations and risk of bias assessments, things like this in Cochrane reviews, you would also have to do a trustworthy assessment. So this truly would move things from this kind of niche activity that is done by a few folk like ourselves into something that anyone doing a Cochrane review would then have to do. You would have to previously assess any of the articles that you were going to include in the systematic review, not to only assess any risk of bias, but previously ask the question, is this work trustworthy enough to be considered at all, or should it be set aside and basically ignored by the review as not sufficiently trustworthy? Incredible resource, a very cool project. What all of these tools and resources teach us, and what participates in my own thinking for my teaching, sorry, I need to move this again, is the idea that yes, there is a technical skill set needed for this. You need to know specific methods, usually starting with something like GRIM. You need kind of general coding skills to be able to make your results reproducible in R, for example, because if you're going to fire some shots at a piece of work, you need to make sure that your own work is reliable and reproducible, usually to a much higher standard. So yes, there is a technical skill set needed, but there is also a much softer and broader set of system knowledge and soft skills. You need first training in recognizing the breadth of these issues, and even kind of to borrow the phrase, kind of red pilling people on the breadth and severity of these things takes training. You also need training in communicating issues that you have found effectively, how to escalate issues to authors, to journals, to research integrity committees, to know what each of those institutions' concerns are, where they tend to drag their heels, how can you motivate them to act, and generally how to work within a resistant system. You also need a lot of help, in my opinion, organizing your own activity, because too many of us get lost in playing detective and take 10 times longer or 50 times longer to critique a given article than we need to. This one is tempting. Once you start, if you sort of take a jump off the deep end into doing this type of sleuthing work, you can very quickly get a little bit obsessed with specific articles that you keep finding deeper and deeper in issues in. And it takes a certain amount of self-regulation and training and social support from a like-minded community to know when to stop, when is enough, and to prioritize your own and organize your own activity to know when to go after what matters. And lastly, to cope with the psychic damage.
Okay, sorry, Ian, just pause for a second.
Sure.
Just been an outage. Maybe research integrity and HR were tuning in to shut you down. 1 second.
If their competence was that high, that would be a good thing. Is that back now?
We hear you. We're just waiting for. There we go. We're back. We're back.
Okay, great.
Yeah, carry on.
So as James says, a certain amount of psychic damage is taken, and this requires an awareness that it's going to happen. I think some people are blindsided by it. Knowing that it's an issue allows you to sort of activate your own support networks and to help put them in place. And all of this is part of the soft skills. Let me give you one example of what I mean by the something from my course on organizing your own activity. There are many, many, many checks that you could do. There's all sorts of things you can look into with an article, and not all of them are worth doing. There are far more effortful checks and far more complex checks and ones that take a lot of time and effort. And there are ones that provide very little scope for your calibration of your own trust, that at the end of the day, you wouldn't really change your mind very much. So even helping others and students and colleagues organize different types of checks into this sort of matrix can help you organize your own activity. Trustworthy assessments that are effective tend to be on the top row. The ones on the left are the best because they're low effort, high reward. The ones on the top right are high effort, high reward, so they can tire you out, but they're still worth doing. The ones on the bottom don't tend to matter that much. And it's useful to introspect and to communicate that many of these different spheres of activity in academia have been defined, but not all of them are worth doing, right? We talk very frequently about whether assumption tests are, whether tests of our statistical assumptions have been violated by analyses. In many, many cases, it doesn't matter that much for inferences. So it's surprising to me that we dedicate classroom time with students to talking about assumption tests when assumption tests are usually not run or reported in the final articles. And even if they were, swapping from parametric to non-parametric often doesn't matter very much. Or complaining about NHST, incredible amounts have been written about it. It often doesn't matter that much. I think it's incredible waste of finite time and brain power, specifically with regard to forensic meta-science concerns. Likewise, small amounts of missing data. Things that do matter a lot, and location is very approximate, are things like stat check, whether test statistics and degrees of freedom can recompute the reported p-values. Granularity and range checks, misinterpretations of p-values, effect size plausibility, and things like this. Tortured phrases, yeah. Computational reproducibility is talked about lots in the last few years, but it is very much on the top right-hand side of this plot. It is very, very useful, and it also will take you dozens, if not hundreds of hours, whereas you might be able to run GrimCheck while making a coffee, as James said. So this is all useful in organizing activity. So these hard and soft skills are taught in these courses that I have put together. They are also open source. I'm still kind of organizing and improving them over time, but the materials are there. I would love to see them taught in other contexts, whether as summer school contexts, For example, I give 2-day workshops, formats of it for PhD students. I also teach it every year as a 14-week master's course, and the materials for both are publicly available. If anyone is interested in having such a course or adapting these materials, or having me give a workshop or giving it yourself, please talk to me. I really think there's a lot of room for this type of teaching at different institutions. Okay, wrapping it up near the end, there are many, many other efforts that we are engaging in that I don't have full time to talk about. You can see hour-long talks about this online. There's 2 or 3 of them on YouTube now. We also with my collaborators, Malta, Ruben, Jamie, I run the ERYOR Reviews Project. It's a bug bounty program for science, and the idea here is to provide consensual, paid, post-publication peer review. So we do this of the most highly cited psychology articles. In part based on an Andrew Gelman blog from last year, we worked out empirically that the top 0.3% of most cited articles in psychology attract 10% of all citations. They are massively, massively overweighted. And it's this top 0.3% of most cited articles, those which have at least 30 citations per year since publication, that we offer this to. So we randomly sample from this list of articles pulled from Crossref, and then approach the authors and offer to do paid post-publication peer review on their article. We say, your work clearly matters. The community says that it matters. It is highly cited. So the most work is building on it. And we think it is worth a second closer look to check if there are any errors in it. We pay them for their time, and we offer bug bounties. So the fewer errors found in the original work, the more we pay to the original authors, and the more errors found, the more we pay to the bug bounty to the reviewers. And then we publish reports online, which are like post-publication peer reviews. We have found errors in every article examined to date, and we also don't think this is problematic. We think this is normal. To err is to human. Small errors in any project, if you look closely enough, you will find them. So we are doing this not as an effort to call out individual papers or even correct them, really. We're doing this to help normalize that that post-publication peer review is done, that it is a worthy contribution in and of itself. To find errors in your work and correct them is not a problem for science. It is a laudable contribution, and we praise authors for their participation, regardless of what's found, especially if they're willing to own up to large issues being found. And in at least one case so far, we have found those things that are a large correction worthy or even a retraction. Strangely enough, I'll say one more thing about error, which is people do decline, despite us offering to pay them for their time, and that this would be an operationalization of the mantra that science is self-correcting. Let me check and correct your science. We get people turning us down all the time. At least 27 people have turned us down to do this, many of which have reasonable things. I don't have time. I'm currently on maternity leave. I've retired even. We find some of these to be less forgivable. For example, one person told us that they already know of an error in their work, which they do not want pointed out publicly. It seems a strange, unscientific position. And another person told us simply, well, their work does not contain errors, so we don't need to search for any errors in it, which was, why didn't everyone else think of that? And then lastly, as this sort of effort to build community, to normalize this type of activity, I run a Slack group called Forensic Metascience in Psychology. This brings together, very importantly for me, multiple R package developers who work in this space, gets them talking more clearly. We validate our tools against one another's, and we try and sort of reduce redundancy between the packages so that they all have clear focuses and good validation. And this has been very fruitful over the last year or two. It also brings together sleuths who are doing this work, and unlike some of the other sleuth Slacks that exist that are held a little closer to the chest and are sort of invite-only things. I also try and include ECRs who have some activity in this space because I think this grassroots activity is very important. The goal here is to build community, to increase internal visibility so that you know who the network of other people doing this type of work is, so that you can come and occasionally gripe and vent some psychic damage that you've taken. And the goal is to turn isolated hobbyists, which is what so many of us were for the last while, into professions, sorry, that should be professionals with networks. It's not a totally open invitation group because obviously some sensitive things are discussed in it. We try to invite people who have at least some record of doing this work with pub peer comments or R package development. But the bar is fairly low, especially for ECRs, if you can sort of demonstrate a commitment in the area. So please do feel free to contact me about invitations. And yeah, James and Nick and many others are in there already. And the Data Colada guys, some of them are there. And Dorothy Bishop and Jack Wilkinson. And yeah, a lot of people within the space are in there. And Sam, of course. Okay. I don't know how much time we have left for questions, but I'm very happy to take them.
Brilliant. Thank you very much, Ian. Very interesting talk. So we are running into a bit of a comfort break that we scheduled, but we will take questions because I'm sure there will be some in the audience. But we'll try and get back up to speed. So are there any questions online or in the audience that you would like to pose to Ian? Okay, yeah, somebody on the side. Hi. Whilst the mic is traveling, I will just say that Ian is at the this is his second talk he's given for the summer school. His first talk is actually available and it delves deeper into error reviews. So if you want to learn more about that, he gave that last year. Really interesting talk and initiative. So do check that out. And we've also got a colleague of his who's speaking on Thursday, Jamie Cummins, who will be talking about checking between pre-registered and published pre-registered protocols and the published article as well. So do tune in for that workshop as well, and he'll give sort of a hands-on walkthrough of that tool. But yeah, let's take your question.
Yeah, so my question is a bit about what can we do in the way that, like, this at the start when you showed the funnel plot, when it was clear that those things were clearly wrong, but because those specific articles hadn't been retracted, that, like, the researchers obviously didn't necessarily say, oh, I'm going to quotations arbitrarily, but air quotes are very strongly around that. Just ignore it. Like, if you're just working with, you're looking through papers and you find something that's inconsistent, my question is a bit like, are you allowed to just discard it? Like, sorry, I'm an undergraduate student, so I've never really done anything like researchy, really. But like, yeah.
No, this is a great question. So my point about not having levers to pull on was exactly this, that up until now, it would be weird to say, and I'm arbitrarily not going to look at those, because there was no mechanism by which I could pull this to say, I'm not looking at this because of this reason. So I sort of had to include it, even when everyone in the room, or maybe no one in the room more problematically, knew that there was an issue. With the advent of a tool like Inspect SR, even though it's still in draft, now you have a mechanism. So you can use it to help organize other activities and to say, well, I am going to look at these articles in the following way. There are like 14 criteria. And even if I don't apply all of them, I say a priori, looking at this funnel plot, there are issues to do with the magnitudes of effect sizes. And here is some work that it refers to on the plausibility of effect sizes. And maybe I'll cite James's book and Ian's course, both of which have content on the plausibility of effect sizes that at least raise questions for the authors. And then I could use content from the course that tell me about things like PubPeer, which is a way of writing comments, even anonymously. If you're early career and you feel a little vulnerable putting your name to it, you can raise questions for the authors and to say, in a non-accusatory way, this effect size seems really, really large for the area or even for the field. Can the authors comment on its accuracy given, these means in SDs? Would it be possible to share the data in some public way? And until those if serious questions are raised, until they are answered, it gives you a mechanism to not include that work. So this is still something in development, right? But we are at least moving towards a set of ways that I have things to point to and levers to pull on to say, I have doubts about this particular work, and for these reasons, I'm setting them aside. And if Cochrane would endorse it, then you would have a really serious player in research synthesis that gives it the blessing by which there is this formalized mechanism of putting aside untrustworthy research. And then we would really have something to work with.
Ian, it's me. I'm still here. I speak to you from beyond the grave. I can think of a single example where that's happened, where I've seen that. I'm sorry I didn't catch your name. That's a really good specific question. There is at least one Cochrane review. What it takes right now is for you to be I can't remember which researcher it was. I think number 2 on the Retraction Watch all-time list. I have seen reviews where that person is cited, the data is implausible, and whoever was doing the review felt like they could safely leave it out and say why they were leaving it out, because this person is on the Mount Rushmore of faking papers. And on that basis, we feel like we could leave it out and just say so. And that's what it takes in the absence of the mechanism that Ian's describing. That's all.
Thank you, James. That was a very welcome intervention there. Do we have another question in real life? Do you have a question, Amelia? Okay, Amelia, you can use your mic privilege and ask your question.
Hey, hello. I don't really know. My question, I don't think it has a good answer, but I'm like a graduate teaching assistant on first year and second year stats, and I work in neuroscience labs. And there's a big gap between what we're teaching the students and their understanding of it, and I would say the understanding of stats among my colleagues. It's much lower amongst my colleagues than what they're being taught. And so and I don't know where that's coming from, but I guess a lot of the errors that you were talking about, the means and the standard deviations, I feel like a lot of PhDs and postdocs wouldn't, in neuroscience, perhaps not in psychology, wouldn't have a meaningful understanding of what those numbers actually are. And I think when we have these discussions about open science, it's quite isolating and kind of a stats nerd sort of thing. And I think we're isolating people who don't have that foundational basis, I guess. And so are you aware of any initiatives to get people to I guess ask questions or be vulnerable about not fully understanding these things before it gets to the point of I've published an erroneous result and I didn't know what I was publishing, if you know what I mean? Yeah, that's my question.
Yeah, there's a really difficult question of power dynamics here, right? Because we are putting students in a position where they have to put their names to articles that report complex statistics or even not complex statistics, like standard deviations, where they are having to take responsibility in a academic requirement sense for the work, while everyone in the room knows, I don't feel like I have a really solid grasp on this. I like to think of courses like the one I teach as supplementary to the stats. It's not about just taking pops at others. It's a way to improve your own work, right? I come out of this with a better understanding of statistics, having seen the here's how to spot if they've been misused, right? Because I can spot in my own work if I'm misusing them or if these things don't add up anymore. So I don't yet know of a formal. I think that the thing you're talking about is necessarily grassroots, about open conversations, about people saying, I don't feel like I have a good grasp on this yet. And that's a very difficult tension, a very difficult uh, needle to thread on the need to get publications for our students, while kind of doing it, learning the statistics in real time, right? And running to stay still. Yeah, I don't have a simple answer for such a complex thing, but like teaching not only of the stats, but of how to spot their misuse and in your own work seem like natural complementary things for me. And that's why I try and teach it that way myself.
Okay, we'll have one more question. I can see people doing a few Irish exits because they're probably dying for a bio break. So we'll have one last one, and then we'll have to say goodbye to Ian.
Sorry, one last question from a non-researcher person. We looked at knowledge, data, statistics, and things like that. But have you seen, since the COVID epidemic, there's a general more awareness among the public in social media about stats, research papers, scientific papers coming up from big pharmas on the veracity about information coming out, research done? Or is this helping you in what you are doing in trying to raise an awareness?
There is definitely a raised awareness, and there is a huge debate raging on whether it is helping or hurting. I think James mentioned this himself. I have conversations with journalists about this every month or two now. When you have the things that are happening in the United States at the moment, where the replication crisis is being mentioned by the Trump administration as a reason for cutting funding. It's hard for this not to enter all of our consciousness, even when they may not be using our findings in a way that we think is justified. That I don't think is a reason not to do it. Equally, yeah, around COVID, there was growing skepticism in useful ways and also in unuseful ways, for example, of the efficacy of vaccines. It's hard to raise the level of consciousness around a given issue and not have some people take a turn that you didn't want them to. It's not a reason not to do it. Sunlight is in general the best disinfectant, in my point of view. I'll keep that answer short because I know you all want coffee. Thank you very much for the opportunity.
Thank you, Ian. So you have, I think, a question directed to you in the chat. So I'll leave you answer that whilst we're all rushing to the toilet and so on. So thank you so much. Shall we all try and give Ian a round of applause? Right. So I'll try and keep time. I'm being very tardy here. So we'll do maybe 10-minute rest break, comfort break.